Today I'll be providing our perspective of the impact of emissions chemistry and meteorology on the wintertime PM2.5 in China. So I'd like to acknowledge my graduate students at Tsinghua University, Zhang and Jia, who had done many of the modeling work, and also my colleague Jiang and his graduate students doing measurement work. So our study was motivated by two questions. First is, for those of you who have living in China for the past 5 years, I think the impression is that air quality has been worse. Indeed, because we don't have the long-term surface monitors, we got the AOD from Moody's for the last 12 years. We focus on winter. We can see that over the high AODs of focused on the North China and also South China. If we pull out the time series of South China AOD, we can see a clear trend of increase. And Yang's talk before me has said that the trend could be due to the emissions. So our question is, what drives the interannual variations? Secondly, in the most recent month, in January 2013, there was very heavy polluted month. So here I'm plotting the 74 stations of PM2.5 observation over China for that month. So the mean is 130 microgram per cubic meter. So the next question is, do we understand the chemical mechanism of these high PM2.5 episodes in January 2013? And of course, we also need to understand what's our current knowledge of precursor emissions and whether it can be confirmed or improved by these new observations. So here I just show some model results compared with the observations. So the model, we use the GEOS-Chem at half-degree resolution. So the emission inventory is, we adopted for this index B inventory for 2006, but we increased NOx emission by 57% to reflect the increase of NOx from 2006 to 2013. But we reduced SO2 by 8% because in the last 5 years, the SO2 has been reported to reduce over China. So that's our model performance, has a very good spatial correlation with observations in terms of monthly mean, but we have a low bias, about 40%. Compared with individual stations, it's about the same. Here I'm showing the PM2.5 at the Tsinghua side. So at that side, the bias is higher, about 60%. So the first question is whether the model can simulate meteorology good enough. We're using the assimilated meteorology, so it's not free running GCM, but we compare relative humidity, temperature, and wind speed at a range of over 100 meteorology sites over North China. So the conclusion is that although there's a systematic bias, which is due to we compare the first layer of meteorology averaged with the point observations, but there's no bias particularly large over the episode days. So we conclude that the model, the no bias over the particularly high concentrations not driven by meteorology errors. Then we look at the PM2.5 concentration measured at Tsinghua site. So that's, this is the observation, and we group it into the clean condition, which has PM2.5 less than 50 microgram per cubic meter, and also the haze condition, and this is our model. So this is sulfate, nitrate, ammonia, organic carbon, black carbon. So we see that about 50% of this aerosol PM2.5 is of secondary origin. As we can see, the inorganics concentrate a great fraction, and this is also consistent with more recent publication of more sites over China. The second observation is that the sulfate has the largest fractional increase and enhancement ratio during that month. So you can see that in the observation, the sulfate ratio actually increased by quite a bit during the haze days. What is puzzling is that the model didn't get that fractional increase. So we think that's something, sulfate is a species we first look at. The first reason we can think of, maybe the emission is too low, then we use the surface SO2 observation to infer SO2 emissions. Indeed, we find that our simulated SO2 is indeed too low compared with the measured SO2. So for North China, we need to increase SO2 emission in the model by 100% in order to match with observations. For South China, we actually need to decrease SO2 emissions by 30% to match observations. Also, to exclude the impact of meteorology, we can actually derive a day-to-day corrective factor to our model to have a perfect match with SO2 observations. So we call this as meteorology correction factors that would take account of planetary boundary, high wind speed, etc. So after we input the improved SO2 emissions and also with the daily correction factors, we run the model again, find out the model still didn't get the increase of SO2, of sulfate fraction increase during the haze, even though the concentration of sulfate is increased by about 50%. So we still didn't solve this puzzle here. So the obvious reason is that we need additional chemical mechanism to explain the missing sulfate formation. So our consideration is that the observation shows that cloud fraction is not significantly higher during the haze days. So that makes us to exclude the possibility of additional in-cloud process responsible for the increase of sulfate during the haze. But we observe that the relative humidity is always higher during the haze episodes. So that have implications for aerosols. So those aerosols will through hygroscopic growth. So that those deliquesced aerosols will have water, and also we think that water inside the aerosols could provide a potential environment for heterogeneity oxidation of SO2. So basically, our idea is that atmospheric aerosols and under high relative humidity, here we said is larger than 50%. So that would create a aqueous surface around the aerosol, so that would uptake SO2 and make sulfate. So we parameterize this rate constant as a function of surface area, and also very critical parameter is uptake coefficient. So here, based on the literature review, we have a lower bound of gamma as 10 to the negative 3, and then the higher bound of 10 to the negative 2. So we then between the relative humidity, I just assume a linear increase of gamma with relative humidity. So after we parameterize that in the model, so we find out the model has a significant higher sulfate concentrations, especially during the high episode days. And also, that's the only way we can increase the sulfate fraction in PM2.5 during the haze episode. Another encouraging thing is that we plot the concentration of PM2.5 and also sulfur fraction as a function of latitude. We can see that the model, after we add the heterogeneous reaction, the increase is predominantly larger over North China. So it didn't screw up the model simulation over South China at all, even though we implemented it uniformly in the model. So that verified that our parameterization, the sensitivity of meteorology and the aerosol surface area is reasonable. We also look at NOx emissions. Turns out NOx emissions are okay, so we don't have a significant bias by comparing with NOx concentration, NO2 measurements over surface, and the nitrate is performing okay compared with observations. Another big issue is with organic carbon and elementary carbon. So after we could increase the emissions easily by a factor 2, still too low compared with observations. But the problem that we only have one site, so it's really hard to scale up the emissions only on the basis of one site. So we just leave it there as a future directions for our group and also for others. The rest of the talk I'll be focused on the impact of meteorology. So our aspect of meteorology is more on large-scale circulations. So the motivation is that, we can run the model using the same emissions by two different months of meteorology. So this is what we see, actually, just by varying the January meteorology, we can see 30% higher PM2.5. And then we look at what's going on in the January 2013. So this is the sea level pressure compared with the climatology over the last 12 years. So this is a climatological location of Siberian High, which is the engine driving this winter monsoon over Asia. We can see that over January 2013, this Siberian High is particularly weak, and combined with the weak Siberian High, we see anomalous southern flow over North China. So we think that's meteorology conditions are favorable for aerosol accumulation and pollution over Asia. So our hypothesis is that we can use the Siberian High as an indicator for this large-scale circulation, and maybe we can build up a relationship with to link PM with large-scale circulation. The beauty of this, that we can use the relationship test CTM and also these chemical climate models. Second, we can project the sensitivity of future PM air quality to climate. So again, this is the time series we see from AOD. We're relying on AOD time series. So first thing we look at is Siberian High intensity. So there's a conventional way of defining Siberian High intensity over a center location in Mongolia. So we took that definition, we call it Siberian High Index. So this is what we got from reanalysis data. In black line is the Siberian High Index, and that is AOD over North China. To our surprise, we found a very poor correlation between this conventional Siberian High Index and AOD. We removed the trend in the time series and normalized it, and still it didn't improve the correlation. So that's suggesting maybe this intentional intensity-based Siberian High Index is not good enough. And then we did a more careful analysis, pick up 2 years. One is a high AOD winter. The next year is a low AOD winter. So we can see that the Siberian High on the 2 years, the intensity didn't change much, but the location has a obvious difference. So in this high AOD winter, the Siberian High is shifted more to the east compared with the low AOD winter. So we proposed a Siberian High position index to as the weighted mean longitude of the center of the Siberian High. So we call it SHPI, it's position-based index. So the unit is in longitude, degree longitude. So we can correlate that with AOD. We find a significant higher and also significant correlation on the interannual year-to-year scale, but also we can find good correlation even on the monthly scale. What is interesting to see is that over January of 2013, which has highest AOD and also highest PM2.5 in the last 12 years, it also has the highest Siberian High position index. So that means that month is a particular unusual is because of the unusual meteorology in terms of, especially unusual in terms of historical content. The correlation improved more if after we detrend and normalize the time series, we could get a correlation of positive correlation of 0.76. Interestingly, over South China, we also find a negative correlation. So that means when you have a higher concentration of aerosol over North China, so less outflow is going to South China. So we actually see a better air quality over South China. So we have a negative correlation over there. So the mechanism that I showed that the wind direction already have a change, have a southerly flow anomaly over when the Siberian High is positioned more to the east. And also, we find a good correlation of this Siberian High position index with relative humidity and precipitation. So those are all favorable conditions for aerosol accumulation. So to summary, we propose a mechanism to explain the missing sulfur formation in winter haze. So it's a heterogeneous uptake and paralyzed on a condition of relative humidity. We find the PM emissions are still underestimated, particularly those emissions of secondary species, and even SO2, we thought we understand emission quite well. Large-scale circulation patterns have a large control on the variability of high PM and low PM years. We proposed a Siberian High position index as an indicator of PM variability over both North China and South China. And use that index, we can explain why January 2013 is the highest, it's the worst pollution year in the last 10 years, because the Siberian High is not only weak, but also potential to the further to the east. We are now looking at CMIP-5 projections of future climate to see like what's the implications of the change in Siberian High position for future air quality over China. So these are the related publication we have, and I'll be happy to take questions if I have time. Thank you. Thank you.
Yes. First, a quick comment on your site in Tsinghua. If that's an urban site, I would be rather careful to bump your model up too much, because you might just completely blow all the region or all sites. That's just a comment. How much do you trust your ammonia emissions that you put in? Because that is maybe one of the critical issues with the Sulfates.
Yeah, that's, well, so first, indeed, we didn't tune up our model to match with the concentration we had at Tsinghua. Compared with that site, our sulfate is still too low by 30%. So that's first. Second, indeed, ammonia is a very important component of PM2.5. We didn't constrain ammonia emissions because lack of observations. Secondly, I think the conventional knowledge is that in winter, maybe ammonia is not a high emission, but now I see evidence saying that this assumption is not right. So we didn't look at that, but it's a good question.